Okay, so now in this example here, we're going to look at the error, the absolute and relative error, when we're dealing with the trapezoidal rule. Okay, so in a previous example of using this integral, we had estimated it using T4. We came up with 11/32 as our approximate value for this integral, okay, from 0 to 1. So now if we look at this as the exact, so we can integrate this easily, excuse me, and we know that from 0, 1 of x squared dx is equal to a third. Okay? And so if we look at the error, right? So look at our error. The absolute error is the absolute value of the actual value, the true value, 1/3, minus the approximated value, which is 11/32. Okay? And so what do we get? Well, when you get common denominator, this is going to equal, what? This is going to equal 32 over 96, or no. Yes. 32 over 96 and minus 33 over 96, which is going to give us the absolute value of 1 over 96, the absolute value of negative 1 over 96, which gives us 1 over 96, which is approximately equal to what? 0.0104. Okay, so that's the absolute error. Now the relative error is the absolute error divided by the true value. So it's going to be the absolute value over the true value, which in this case is going to be 1/3. So it's going to be 196 over 1/3. And of course, this is going to end up being 196 times 3. So we can write this as 3/96. Okay, which is going to give us what? 0.03125. 0.03125, right? Or we can write this as a percentage, right? So we can write this as a percentage, which is 3.125%, or, you could say approximately 3.1%. Okay? Okay, so now compare this to what we got with the midpoint rule. The midpoint rule gave us about 1.5% error. And the trapezoidal rule gave us 3% error. So this confirms what we suspected when we talked about earlier about the midpoint rule being a better estimate overall than the trapezoidal method, or the trapezoidal rule. Okay, so there's some evidence to support our hypothesis, if you will, what we suspected. Okay, see you next time.